A very good day, everyone. In our last lecture, we considered some of the basic operations of the operational amplifiers, and then we talked about the integrator, differentiator, and the adder. And now we are going to be considering the non-ideal op-amp. So let's place this as introduction. So non-ideal op-amp. So let's recall the op-amp model, where we have the input resistor and the voltage control source in parallel, connected in parallel with the output voltage. And then we know this gives us the op-amp model. This is connected to ground. So this is the non-inverting input, this is the inverting input, so this is V sub P, this is V sub N. And the differential voltage is V sub N, so this is R in, and this is AV in, and then this is V out, and this is the output resistance. Here we know that I sub P flows through this terminal, I sub N flows through this terminal, which is 0. Okay, she's asking to be 0. Okay. Now, in the case of the ideal op-amp, just like we've already covered in the previous lecture, we're able to consider the current constraint and the voltage constraint. And some assumptions were made for the ideal op-amp. I sub P is the same as I sub N is the same as 0, which implies that no current flows into the op-amp input terminals. Okay, meaning this current flowing through the non-inverting and the inverting terminals is 0, such that the input resistance is seen to be infinite value, because if the input resistance is sufficiently large, meaning it's an open circuit, then no current will flow. And also, the differential input voltage is seen to be 0, for which V sub N being the same as the difference between the point voltages or the node voltages is 0, so that V sub P is the same as V sub N. Therefore, V naught is the same as A V in, for which the open loop gain, is some infinite value, and then the output resistance is the same as 0. Okay, and we also established that if V in is 0, V in is 0, then V out will be 0, because 8 times 0 is 0. But in practical or non-ideal or practical op-amps, we have that the input resistance could be as large as 2 mega ohms, but not infinite, because we can achieve that in practice. And the output resistance is some value of 275 ohms, which is not the same as 0, which is not a complete short circuit. And then the open loop gain could be as high as 200 1000, and the common mode rejection ratio could range between 60 dB to up to 90 dB. Now, in addition to the op-amp parameters mentioned in part 1 of the series, some other parameters that may be considered when characterizing the performance of op-amps are some other terminologies, okay? Let's just consider some other terminologies. So the first of which is the input offset voltage. Now, in ideal op-amps, for a zero input voltage, Vin equal to 0, then the output voltage is also equal to 0 because V0 is the same as AVin, right? But in the case of non-ideal, this is in the case of an ideal op-amp, okay? But when we consider non-ideal op-amps, there may be a small direct current voltage at the output, even when there is no differential input voltage applied. So therefore, the input offset voltage is the DC voltage that must be applied between the input terminals of the op-amp. To reduce the DC output voltage to 0. Okay. And now we also have the input bias current. Now, the input bias current is the average of the DC currents flowing into the input terminal. So that is I sub B is the same as I sub P plus I sub N divided by 2. And then we also have the input offset current, which is the difference between the non-inverting input and the inverting current input. So this is a small difference in the bias current from one input to the other of the op-amp. So we can say that the input offset current is the same as positive negative modulus I sub P minus I sub N. Then some other terminologies are the input common mode linear range. So we have input mode linear range. And this is the maximum positive or negative voltage that can be applied to the op-amp inputs and still have a linear circuit operation. And we also have the input differential range, which is the maximum differential signal that can be applied to the input terminals of the op-amp without degrading its characteristic. And also, we have the power supply rejection ratio, which is the ratio between the supply voltage and the input voltage. So we have to talk about the change in the input supply voltage to the change in the input voltage. So in decibel, the power supply rejection ratio is given as 20 log to base 10, change in the supply voltage to change in the input voltage. Then we also have the maximum output voltage swing, I don't know, output voltage swing, which is the maximum linear positive or negative output voltage allowed in an op-amp before nonlinear effect due to the transistor saturation or cutoff occurs. And the last we'll be considering here among other parameters is the slew rate. And this indicates how fast the output of the op-amp can change with respect to time. It's usually expressed in volts per microsecond. So let us consider a simple example. Here we have disconnected to the inverting input. And then have the feedback resistor. And the non-inverting input is grounded. And then we have the inverting input connected to some voltage source. Let's say this is 2 volts. Let's say this is 1K ohm. Let's say this is 5K ohm. And this is okay. And now you'll recall that we already established that if this is Vn and this is Vp, I sub n 0, right? Then I sub p 0 volts is 0 ampere. And now if that is true, then it means the entire current will flow in this direction. And we know that this is the reference voltage. Ground is 0 volts. The reference voltage is 0 volts, right? Now, we know that in an ideal op-amp, V sub P is not the same as V sub N. But in this case, V sub P is the same as the reference voltage, which is 0 volts, right? And V sub N is not the same as V sub P. So if we write Ohm's law at the input side, okay, at the input side, Ohm's law. So we have at this terminal, this is positive, this terminal is positive with respect to ground, so that's the 2 volts, yeah? So Ohm's law at the input will be I, the current flowing through the 1K ohm, with the difference between these potentials, which is 2 minus V sub N, which is over 1K. And Ohm's law, this is at the input. So Ohm's law at the output will be this other half between V sub N and V naught. So I will be the same as V sub N minus V naught divided by 5K. Okay, so let's say this is our first equation and this is our second equation. And also recall that the output voltage this time is the same as AV N, which is the same as A into bracket V sub P minus V sub N. And we already know that V sub P is 0 since it is at ground potential. So V naught will be the same as negative A V sub N. Okay, so let's say this is our third equation. But you'll observe that equation 1 and 2 are comparable such that 2 minus V sub N of 1K is the same as V sub N minus V naught over 5K. And if we work this through, this is 5,000 times this 1,000 times this process here. So this will give us 6,000 V sub N equal to 1,000 V naught plus 10,000. So V sub N will give us V naught plus 10 divided by 6. Okay, So this is our fourth equation. Now, if we put the fourth equation into our third equation, then if we put 4 into 3, then V naught will be the same as negative A into bracket V naught plus 10 divided by 6. So if we open this up, then you will see or observe that V naught is the same as negative V naught over 6A minus 10 over 6A. So if we bring this crosses equality sign, then can make a V naught the subject of formula here. So that will be V naught will be to bracket 1 plus A over 6, right? It should be equal to negative 10 over 6. So V naught here will be the same as negative 10 over 6A divided by 1 plus A over 6. Now, if A is the same, say 200,000, then V naught will be the same as negative 10 over 6 times 200,000 divided by 1 plus 200,000 divided by 6. And this will give us negative 9.997 volts. V naught. Now, if we should consider the ideal scenario, let's consider the ideal scenario. So, ideal op amp, for instance. You agree with me, based on the assumption that Vp is the same as Vn, and Vp is 0, so Vn is 0. So, this expression here will reduce to mean this expression, right? Will reduce, which compares equation 1 and 2 being the same, being the current flowing through, will be negative V sub n over 1k equal to, because V sub n is 0, then negative V naught over 5k. And in this case, oh no, this will be 2, not 2. Because this is 0, so this reduces to 0, so that will be 2 over 1k. This reduces 0, negative V naught, so that V naught will be 20k, 10k, oh my goodness, 10k. That's 5 times 2 is 10k divided by 1k, which is equal to 10. So V naught is equal to 10 for the ideal case. And you see that in the non-ideal case, it is close to the ideal value, but some approximate value. But should we assume that V naught, or better still, this expression V naught, let's change the color. So recall that here we already have V naught to be equal to this expression. And in the ideal case also, in the ideal case, A is some infinite value. And if we plug that in here, you observe that 1 will be far, far less than A over 6, such that V naught will be the same as negative 10. This will be negative here, okay? Negative, so it's negative 10. Because V negative minus, so negative V naught, so negative 10 over this, that will be negative 10. This will be negative 10, okay? So this now will be negative 10 over 6A divided by A over 6. So this will cross this will cross this. So in other words, as the open loop gain approaches some infinite value, then the non-ideal model V0 will model the ideal scenario, folks. Right? Perfect. But in a more practical sense, this circuit can be modeled as follows.